So, um, why does structure matter? Why do we care how atoms orient themselves in three-dimensional space? Okay. And so now we're kind of getting into the application phase of this unit where the stuff that we learn about, everything builds on itself, especially in this unit, but you're going to start to see more and more applications of it. So molecules behave in certain ways based on how they orient themselves and by their molecular polarity. And so polarity is going to be determined by what is connected to what. So that's why you have to know your Lewis diagram, and then the overall molecular shape. All right. A bond can either be polar or nonpolar, and a molecule can either be polar or nonpolar. And so we'll kind of see how it matters whether or not you have polar or nonpolar bonds, which can then determine whether or not you have a polar or nonpolar molecule. You'll see me abbreviate P for polar and NP for nonpolar. In your lab, you guys will be looking at the whole molecule polarity, but in order to do that, sometimes you have to decide if a bond is polar or nonpolar first. So that is kind of what we're going to be working towards. We're going to be working towards identifying whether something is polar or nonpolar. Before we kind of get into that, the 3.4 lesson is on like bond characteristics, so bond length, but then also bond polarity. And when we talked about like atomic size, you know, we like the trend of atomic size. We talked about how as you go down the periodic table, atomic size gets bigger, and as you go across a period, it gets smaller. And this is just to remind you that atoms that are bigger will have a longer bond length. Okay, so if that can be measured. But this will also affect kind of bond polarity. How polar something is and how big something is can determine its electronegativity value, which contributes to the bond polarity and molecular polarity. So this is just to remind you that you still kind of have to understand atomic radius and the general trend at times to be able to compare stuff. Also, if you have higher bond order, remember bond order is like, do you have a single, double, or triple bond? If you're sharing more electrons, then it's actually going to reduce the bond length. And it's going to make them stronger. It should not be surprising that, like, did ever you guys play Red Rover? Like, was that still a game, like, when you were growing up where you, like, hold hands? Some of you are nodding, but some of you aren't. Where you hold hands in a chain and then you go, you know, you cross another team and the other team yells, you know, Red Rover, send Betty right over, okay? And then Betty runs and tries to like break through, okay? And if she breaks through, then she gets to take someone back to their team. But if your team's only down to 2 people, you get to hold both of your hands together, and that makes it harder to break, okay? Like through. So it's like more difficult to win at the very end, much like you would imagine. You want to think of like a single bond as like grabbing one person's hand, but a double bond would be grabbing 2 people's hands, and it would be a stronger. It also shortens the bond length though, because the electrons are pulled tighter, and that, you know, attractive force to hold kind of all those electrons in, it's going to require more energy to break those bonds. So when we talk about like chemical reactions, and then when we get later into the year into like energy and stuff, this will come in handy to kind of remember. So bond polarity is based off of how electrons are shared in that bond. And in covalent bonds, we kind of talked about, we started this unit saying, okay, well, electrons are shared, and that's what we've been learning about, but like how well are they shared? Are they shared evenly or unevenly? Okay, but when electronegativities are not equal, the sharing is also not equal. Okay, so we haven't been drawing this so far, but it's an important idea to explore. A polar bond is where one of the electrons, or sorry, not where, is one where the electrons are not shared evenly due to electronegativity differences, and polarity will increase as the difference in electronegativity increases, and it creates what's called a dipole moment, which is a vector. And so when you see something like you got H2 here, this is a nonpolar covalent bond. The electronegativities of both hydrogens are the same, and so the electrons being shared are even. They spend equal amount of time close to both nuclei. But if you have something like HCl, where hydrogen has an electronegativity value of 2.1 and chlorine is, I think it's 3.5. Let's look. Let's double check. Okay, I was right first, 3. All right, it's a full drop. But it's still, you don't have the same electronegativity value here. Chlorine is going to pull the electrons closer. And so a dipole moment gets written as an arrow, as you can see here. And the arrow points towards the more negative end, and then the positive end of the molecule is with the, like the arrow with the plus sign. Meaning the electrons are going to spend more time next to the chlorine than the hydrogen. That's going to make this molecule polar as well. You're going to see this little symbol, and it's a lowercase delta, and it means partial. So this molecule is going to have a partial positive and a partial negative. It's not fully ionized. The electrons are still shared because there isn't a great enough electronegativity difference for it to be characterized as an ionic bond, where you have like a metal transferring the electrons to a nonmetal. But it's not a nonpolar covalent bond because the electrons are not shared totally evenly. It's kind of in between, so it's partially charged. Okay, and that's going to have this molecule would orient itself accordingly in a electric field, and it would line up with the chlorines attracted to the positive plate and the hydrogens attracted to a negative plate. And that's how, like, scientists started to characterize molecules as polar as nonpolars. They saw how they would behave in like a magnetic or an electrical field. Okay, so you can compare the polarity of different bonds just by looking at electronegativity values. So if we were to figure out, okay, a carbon-nitrogen bond, carbon has an electronegativity value of 2.5, nitrogen 3.0, that's a difference of 0.5, okay? And it would, the dipole moment would go towards the nitrogen in a carbon-nitrogen bond, that the nitrogen being more electronegative. For sulfur, you've got 2.5 and fluorine 4.0, so it would be a bigger dipole moment towards the fluorine with a difference of 1.5 there. The nitrogen, again, being 2.5 and the phosphorus being 2.1. So not a large difference, but still, in this case, it would be pointed towards the nitrogen, again, being the more electronegative. Okay, and so if you were like, okay, which is the most polar, you'd put the sulfur fluorine one as first, and then the carbon nitrogen. So you can talk about how polar or how uneven the electrons are shared. You could draw representative dipole moments accordingly. So that's just what you need to know when you're evaluating like individual bonds. Okay. There, if you go and look up bond polarity differences, you will see that different texts have different guidelines, and there's different scale values, because remember, electronegativity is a scaled value. And I taught you guys the Linus Pauling scaling, which is from 0 to 4, and that's just one one scale. It's the most popular scale to rank electronegativity, but it is not the only one. And so there are just some people that will say that pure covalent is, you know, less than 0.4. Other people will say less than 0.5. Some people will say polar covalence between 0.5 and 2.1 and not 1.8 here. So it's more important that you know that if you have no difference, okay, it's a pure covalent bond, nonpolar covalent bond shared evenly. If you have any kind of difference, some difference, and I would say between non-metal atoms, you're going to have a polar covalent bond. Now, it really does need to be bigger than 0.4. If you just have like a 0.1, 0.2, 0.3, and even borderline 0.4 difference, it's very, very, it's a weak polar bond, and most people will characterize that as it's shared pretty evenly enough to be considered non-polar. But then if you have a large difference, and this is where you'll see between metals and non-metals, that's where we'll see electrons being transferred. And yeah, you don't have to memorize these. You more want to look at, well, we're only in the covalent unit, so you're not going to see metals bonding with non-metals yet. And so you want to see, is the difference basically bigger than 0.4? And we're going to characterize that bond as a polar covalent bond there, okay? And then when we get into ionic, we will characterize it. But it's just important that you guys know that bonding is on a range. Remember, I started off the unit saying that chemical bonding, there's no like simple answer. It's some kind of attractive force that makes the atoms behave as a unit, but how they behave is really dependent on what's there and how it's arranged, and you're getting into the complexities of it. So understanding this idea of bond polarity leads us to this idea of molecular polarity, the whole molecule. Okay, so molecule, the whole thing depends on both bond polarity and the shape. So that's why we've covered shape in this idea of bond polarity. If the molecule is diatomic, the bond polarity is the molecule polarity, meaning like that H2, you had a nonpolar bond, so the molecule is nonpolar. When we had the HCl, the bond was polar, so the molecule is polar, because that's the only thing that you can base it off of. If the molecule has more than one bond, the polarity of each bond must be considered in the context of shape and other bonds. So you have to look at all your dipole moments, if you have more than one, and if there are lone pairs of electrons. So how do you know if the molecule is polar? Not all of the attachments to the central atom are the same element. That's a big giveaway. There is one lone pair causing the structure to be unbalanced. Big giveaway. The dipole may or may not point towards the lone pair. When there is more than one lone pair, you have to consider the resulting shape. So polarity is like this is definitely something that requires thinking, okay? Some molecules you can look at and just see, but you do have to kind of think through these aspects. And I have a great video on the 3.5 lesson that really, if you need like a quick like reminder for polarity, it goes through everything so well and succinct. That would even be faster than going and finding like what I'm talking through here, okay? So shapes that are worth talking about for polarity, and you just get better at it with practice. Tetrahedral is worth mentioning because it's important for you to know that no two attachments are directly across from one another. So even if you had like CH2 and then the other side was like Br and Br, like the molecule written out, let me do the Lewis structure. If you do the Lewis structure, and you have H2 and Br2, the Lewis structure can make it look like it can be symmetrical, okay? Or if you were to draw it like putting the H's opposite of each other, like it looks like it would kind of balance out, but this would be a polar molecule, okay? So tetrahedral, if you have one thing that's different, like if it's all the same thing, it's going to be nonpolar for tetrahedral because all the dipoles will cancel each other out. But if you have one different thing or two different things, it's going to make the molecule polar, okay? Assuming you have enough of an electronegativity difference. So it's worth mentioning tetrahedral that none of the attachments are directly across from each other, so they do not cancel. It doesn't matter, like you can't put the bromine any position that it would cancel out the other bromine moment of it. So for every molecule, okay, you have to determine the polarity of the whole molecule, all right? For water, and I like this image because it kind of shows the redder the color, the more electron rich it is, and then this blue is kind of like cold to electrons. There's not a lot of electrons. Polar molecules are sticky molecules, and they have, you can see this partial positive, partial negative. You've got the dipole moment with water going upwards for it, and it has these two lone pairs of electrons on the central atom, and that's going to make it very unevenly distributed because the hybridization is sp3, and so that's the electron geometry for, even if we were to draw it like this, okay? So we don't normally draw like water like this, but it's important for you guys to see. It doesn't matter where I put the hydrogens versus the lone pairs of electrons. Remember I said that the tetrahedral shape, no two attachments are directly across from one another. So even though it looks like, oh, these electrons here are going to balance each other out, they do not. They're not faced the same direction. Plus, when we draw water with the bent shape like so, this is a polar bond here. So you'd have a dipole moment towards the oxygen. This is a polar bond towards the oxygen. If you were to add your dipoles, okay, so you take one and then the other, this is where they get the overall vector for the overall dipole moment of the molecule. So you can look at the individual bonds, and if they are polar, then you can then, if you remember your vector addition, the kind of the general idea of it, lining the tail to tip region of it from your force and motion class, then you can kind of think about if that way makes sense for you. This is going to have a dipole moment. If a molecule has dipoles that do not cancel each other out, it's going to make the molecule polar. Versus, okay, CO2, which does have polar bonds. So oxygen has electronegativity of 3.5, carbon's 2.1. So it has dipole moments towards the oxygens, but they cancel each other because if you have one vector going this way and then the other going this way, they're going to cancel each other out and you have no dipole moment overall, which makes this molecule nonpolar. So it can have polar bonds, but still be a nonpolar molecule if all of the bonds kind of cancel each other out in terms of their orientation. So this one with the CH3Cl, if you have one difference here, and this is important to note, a carbon-hydrogen bond is considered a nonpolar bond. It has, carbon is 2.5 and hydrogen is 2.1. It's worth mentioning that if you only have, okay, if your molecule only has hydrogens and carbons in it, nothing else, it will be a nonpolar molecule. Always. Always. Okay. So that's why you're not seeing, they're drawing just the dipole moment from the chlorine to the, from the carbon to the chlorine there, because that has a large electronegativity difference. These have a difference in electronegativity of 0.4, and that's not considered to be polar. A carbon hydrogen bond is not considered to be a polar bond. Versus if you have carbon tetrachloride here, this is a very non-polar molecule because you have the same thing attached 4 different ways, and so all the electrons are going to be distributed evenly, and that's going to make the molecule very non-polar. But on a tetrahedral shape, all 4 things have to be the same in order for it to be non-polar. Okay? All right. We still have plenty of class time left.